Okay, I first want to ask a question. No, we're ready. We're going. Okay, so we said this on the first day, that calculus is about two fundamental problems. You know how much of something there is, you want to know how fast it's changing. You know how fast something's changing, and you want to know how much of it there is. So what I want you to think about for a minute is the mastery test. All this algebra that we're doing in the mastery test, all these rules we're memorizing, how does it fit into this? How does it fit into this? The calculus is either about, you know how much of something there is, you want to know how fast it's changing, you know how fast something is changing, and you want to know how much of it there is. Okay? So, talk with the person next to you, 1 minute. What does the mastery test have to do with this? Okay. So tell me, what do you think? What does the mastery test have to do with this overview? This is a very broad overview of calculus, but it's everything in calculus is about this. So what does the mastery test have to do with this? What do you think? Austin, what did you say?
We know how much something there is, and we need to know how fast it's changing at a specific point.
Okay, he's saying that it has to do with this first bullet point. Agree or disagree?
Agreed.
He says it has to do with this bullet point. Agree with that? Okay. Someone else, can you say more about that? Christian?
Not only is how much something there is and you want to know how fast it's changing, but it's like a bunch of things changing together because it's like an equation. So it's like more than we have to like derive two things at once, like either the product rule or the chain rule, like the quotient rule.
Okay.
Those things are changing together.
Okay. What else? Is that a hand, Ariana? Nice and loud, sorry.
Is that whole point for the stars? Is that like the accumulation?
So, okay, so you know how much of something there is and you want to know how fast it's changing. Where do we see accumulation function in that? Nicholas?
Do you know how much of something there is?
Right, that's accumulation, right? And on the mastery exam, where did you see accumulation functions?
It'd be like your f of x.
Given functions, right? So all those functions I was giving you was an accumulation function, right? A quantity function. And then all these rules are to determine an exact rate function or a closed form. So the rules are like a fast track to getting a rate of change function that can rapidly output rates of change without having to go through the whole thinking through the process of it, right? It's just you plug in an x, it spits out the rate at that x, right? And then you can plug in another x, it spits out the rate at another x, okay? And so the journey we're on right now, is it differential calculus or integral calculus? We're doing differential calculus. We've got accumulation functions, we're determining, and we're talking about rate of change functions. So currently, right now, we're looking at rates of change functions that we've just, we found this way to get rates of change functions easily. So now we're looking at rates of change functions and we're inferring about the accumulation. Okay, that's what we did in your homework, and we did on Wednesday, and we're going to keep doing that. Okay, but so now we're in this kind of mode of differential calculus. But we're soon going to see that what you did on the mastery has a lot to do with integral calculus too. Okay, and that's when we're going to, at the end of the course, we bring this whole thing full circle. Okay, and that's what the fundamental theorem of calculus is that these are both two sides of the same coin, and your mastery, all these mastery rules that you learn are going to be equally as important when we turn back and look at integral calculus again. Okay, so at the end of class last time, we had kind of looked at the rate, and we said that we came up with an accumulation function. This red one. So I'm going to send this thing going again. This is the same one. And so this is showing, again, x changing. That's the value of n is x. And then I'm showing the rate, the current rate. And now I'm giving you a visual of that rate also with the blue tangent line. Okay, so I want you to answer each of these questions. So the first question is, where is the accumulation of f decreasing, and how can you tell? And so there's actually two ways in this whole, what I'm showing you here, that you could conclude that, or deduce where the accumulation is decreasing. All right, so have a conversation. Go. F is the accumulation. F is the accumulation function. That's the red graph.
But I found that since the rate was going down, but you're still accumulating it slower, so you're still accumulating
Okay, so this is supposed to be the easy question. How did we do? So where's the accumulation decreasing, and how do you know? Janae? What goes below the x-axis? So you're saying wherever the red graph is below the x-axis is where the accumulation is decreasing. What do we think about that?
I think it's when it's going down.
When it's going.
When the slope of the line is.
So it is a four-letter word today. You can't use it because there's so many quantities and graphs and equations. You got to specify. Don't say it. You specify exactly what you're talking about. Okay.
When f of x is decreasing.
Okay. So
the y, of course, is decreasing on that graph.
Okay.
So from 2 to, I guess, 0.7 or something.
Is that what you meant to say when you pulled those numbers off? From where to where?
Or negative 2 to 0.7 or something. Yeah.
Okay, so you're looking around here somewhere?
Yeah.
Like maybe here?
Negative 2.5.
This is negative.
Yeah, 1.5. Yeah.
Okay, maybe around here?
Yeah.
Okay, and maybe around here?
Yeah, that's what I meant.
Okay, fair enough. So he's saying that, so you're saying from here to here the accumulation is decreasing.
Yeah, when the f of x function is going down.
So he's saying, he's looking at the graph itself, he's saying it's going down, therefore accumulation is decreasing. Is there another way to see that accumulation is decreasing? Gilbert?
If you were to graph the...
No, not if you were to graph. From what I'm showing you, is there another way to see it?
balance.
Okay. Alexander?
The rate function, tangent line is negative at that interval.
Okay. So you're looking at this?
Yes.
Yeah, this is the rate.
Yes.
So right at this point, what happens to the rate?
It's a negative rate.
It's negative, and it's negative until the accumulation does what? Starts to, no, not positive. So the accumulation starts to increase, right? So when the rate is negative, starting right now, the rate is negative, our accumulation is decreasing, it's going down. Until the accumulation starts going back up again, and that's when the rate turns positive. So does that make sense to everybody? That's the easy part. It's going to start getting confusing quick, so we got to make sure we got the easy part done. All right, so now, next question. Where is the rate of change decreasing? And that means one of two things. The rate is becoming something or something. And then if the rate is decreasing, what can you say? Or let's just do question 2. Let's just do question 2 for now. Go. Question 2. Go.
Yes, become negative.
It's going down here.
Okay, somebody new. Where do you think the rate, Sean, where do you think the rate is decreasing?
It's decreasing through the whole thing up to 1.1.
Up to 1 point, all the way to here? Where am I? You're saying all the way to here?
Yeah, because as it goes up that slope, it's getting less steep,
Okay.
and then then it starts turning negative. But once it gets to 1.1, then it's getting steeper and increasing.
Okay, what do we agree with that?
You say from negative to negative 2.
We're just looking at -4 to 2. So you're saying from -4 to 1.1, the rate is decreasing. Agree? Aaron?
I think it's from -4 to 0.
-4 to 0. Well, let's look. Is it still decreasing now? Now? Okay, still decreasing. What about now?
Well, no.
So here it's -0.3 and then -6.2. Decreasing or increasing? -6.3, -6.2. That's an increase, right? So right around here, what happens to the rate? It starts to increase. So you had the right idea, you just went too far. So it's from -4 to something like -0.1 or -0.2. Okay, and so there's two ways that can happen. So what are the two ways that can happen, that the rate is decreasing? Anyone get what I was getting at here?
Like it's because it's starting to level up to 0.
Well, nothing ever becomes 0 with that rate as it's decreasing. What's that?
Less negative.
What happens here? So yeah, how is it decreasing here? The rate's becoming,
More negative or less positive.
which is it?
Less positive.
Isn't it becoming less positive here? The rate is positive, becoming less positive. And how else can the rate decrease? Is it decreasing through here? How is it decreasing? By becoming more negative, right? So the rate can decrease by becoming less positive or more negative, but it's always decreasing there. You see? It starts at 34, it goes down to 0, and then it keeps going down to -6 or -6.3, something like that. So when the rate is decreasing, what does that tell us about, is the accumulation function increasing or decreasing when the rate is decreasing? When the rate is decreasing, is the accumulation function increasing or decreasing? Could be either, right? When the rate's becoming less positive,
It's still increasing.
the accumulation's increasing. When the rate's becoming more negative, the accumulation is decreasing, you see? Okay, next question. If Rx is decreasing, that's what we're talking about, right? We just found out that from -4 until about -0.2, it's decreasing. So what can you say about the rate of change of R? If R is decreasing, think of R as a function. If R is decreasing, then what can you say about the rate of change of R? So what did we say up here? We said if the rate of change of F is negative, then the accumulation is decreasing. It's now we're saying that R is decreasing. What can you say about the rate of change of R? Peter?
It's negative.
Yeah, isn't it the same thing as this? So just forget that R is a rate. It's just another function, right? And so if R is decreasing, then what about its rate? It has to be negative, right? What about the graph of F? So now we're going the other way. So if R is decreasing, we just said that its rate, the rate of R must be negative all through here. What about the graph of F when the rate R is decreasing? What can you say about the graph of F? Is there anything we can conclude? The graph of the accumulation.
Like about the curve?
Yeah,
Well, it would never be, I don't know how to say this, but it'd never be like sloped like
Right.
that.
Right. So even though it goes up here and it goes down, there's something in common about this whole part of the graph. It's like, which way does it turn, right? The graph is turning, which way?
Down.
Yeah, it's turning down, or it's turning like clockwise. Do you see that? Whether it's going up or going down, if the rate is decreasing, it's always bending down. It's always turning down. We call that concave down. Or turning clockwise. The graph is turning clockwise from left to right. We can call that concave down. Doesn't make sense, right? Because the rate is decreasing, getting less positive or more negative. It's always bending down, whether it's going up or going down. It's always bending down, right? Okay, does it make sense?
Concave down.
Concave down. Like a, what?
Potato chip.
Well, I get lots of practice at frowns these days with Emma. She frowns. Okay. Concave down like a frown, okay? All right, so then I've got another one here. So right now, we've got our accumulation functions called f. R1 is the derivative of f. R2 is the derivative of R1. I'm showing you the value of R2 at -3. So x is -3. R2 is 7.2. So now I want you to talk. What can you conclude about R1? And what can you conclude about f? Go. What can you conclude about R1? And what can you conclude about f based on what we just said?
So R1 is changing.
Positive for negative. It could be going up too.
So it could be like.
Don't look at these yet. Focus here. Okay, I'll tell you.
Take down means that, yeah.
Okay, just put a face down. Forget about what you're looking. Focus here. Focus here. Okay, what do we think? So, what do we see about R2? It's positive. It's the rate of change of R1, and it's positive. So what can you say about R1?
It is also positive.
That it's also positive, right? No. It's the rate of R1. If the rate of R1 is positive, then what can we say about R1? It's increasing, right? It's increasing. It's two different things, though. It's two different things. It's giving me this weird thing. Okay, increasing. So, what can you conclude about F? If the rate of change is increasing, then what at this moment here, what can we conclude about F?
The accumulation of F is getting bigger, or it's increasing.
The accumulation is increasing. Is the accumulation increasing? If the rate is increasing? Aaron, why not?
It just means that the rate is increasing, so it's concave up, but it can still be negative. Or it could still
What
be-
could still be what?
The accumulation could still be negative or decreasing, but since the rate is increasing, the shape will be concave up. It will be headed towards the
So in this situation, could the function f be decreasing? Is it possible that it's decreasing if the rate is increasing?
Yes.
Draw with your finger. The rate is increasing, but the accumulation is decreasing. And could the accumulation be increasing if the rate is increasing? Right. It could be either. So, but we do know for sure what do we know for sure about f?
That is positive.
Concave up. Right. Concave up, like a cup. So we don't know. We don't know if it's, all through here, the rate is increasing because here it's becoming what? The rate is becoming less negative, and then here it's becoming more positive. All those situations are an increasing rate, and here the accumulation is decreasing, and here it's increasing. Okay, so now let's turn on R1. So I'm going to show you what R1 is at this value. Maybe. It won't give me another thing here. I want to give me another command line. It's going to make things difficult. I can't show you what R1 is. Oh, because caps lock is on. Okay, now talk. So now I'm showing you at this point, at x equals -3, I've showed you R1 as well. So what can you conclude? Chloe, what do you think? So well, let's not talk, let's just go. So what do you think now about what's happening at -3?
It's the point where it changes from being, it's where this,
No it. No it.
okay, but the slope slope of R1 is 0, so the point where R1 goes from having a negative slope to a positive slope.
I'm not sure if you're looking at the right thing there. Do you see what I just put up? I just put up what the value of R1 is.
Oh, sorry. Okay. At negative 3.1.
Right.
Okay. So that means that the graph should then, instead of being in the second quadrant, should be in the third quadrant.
If it doesn't, the rates don't tell us what the value of accumulation is. It only tells us how the accumulation is changing. So it could be negative or positive. But I kind of put you on the spot and give you time to think. So, does that make sense?
Yeah.
Knowing the rates doesn't tell us if the accumulation is negative 100 or positive 100 at this moment. But it does tell us how the rate is changing. So how can we conclude if we know that R1 is negative 7 and R2 is positive 7? What can you say about the accumulation at this moment? Alexander?
I'm not sure.
Oh, then forget about R2. R1's negative. So what's happening in accumulation? Decreasing. Decreasing. R2 is positive. So what's happening to R1?
It's just increasing more.
R2 is positive. What's happening to R1? Increasing. So the rate of change, or the accumulation is decreasing, and the rate is, what does it look like here?
Would you say that the accumulation is decreasing?
Yeah, but let's say them separately. Don't use these phrases because it gets confusing. So the accumulation is doing what? Decreasing. And the rate of change is? Increasing. So draw with your finger. What does it look like? All right, so quickly, I'm just going to throw out something over here. So now, positive 3. Go. What's happening? Positive 3.
They're both increasing.
Molly, go ahead.
Oh, it's just increasing.
No, it. Not allowed.
Slope is increasing.
Slope is
Wait,
increasing.
sorry.
We're talking about the accumulation.
Oh,
What is what's the accumulation doing?
And R1 and R2 are supposed to be the same? Or about the same?
Yeah, but that's, there we go. How about that 5?
Well, it's accumulating. Wait, it's accumulating less.
Aaron.
So R1, the accumulation is a positive increase, but then when you move to R2, it starts to decrease. The accumulation starts decreasing, the rate.
No, that's not right. What can we say about the accumulation? Ross.
Accumulation is increasing.
And how do you see that? From what?
From R1.
R1 tells us, because it's positive, that the accumulation is increasing. Okay, good. And what else?
The rate of R1 is increasing.
The rate is also increasing, which means about the accumulation, what?
Is accumulating faster.
Accumulating faster, and so the graph would be?
It's like
Right. So we have there's our accumulation function. Over here we said the accumulation was, or the rate was, actually the rate was negative. First I showed you that the accumulation, first I showed you that R2 was negative. And so we said, oh, that either means that the rate of change is becoming less positive. First I showed you that the rate was, R2 was positive. R2 was positive. So that meant that the rate was either becoming less negative or more positive, because it's increasing. And then I showed you that the rate was negative. And so then that meant it had to be getting less, that the rate of change was getting less negative. And then I showed you over here that they're both positive. So that means that the accumulation is increasing because R1 is positive, and the rate, since R2 is positive, also the rate of change is increasing, meaning it's getting, the rate of change is getting more positive. So that's concave up. Okay, so now that you're on your worksheets, or no, actually, before your worksheets, one more thing. So what we're talking about here is what's called this, the rate of change of the rate of f, right? So we're taking the rate of f as its own function, and we're taking the derivative of it, the derivative of the derivative. This is called the second derivative, okay? This is called the second derivative. And these are all notations for the second derivative. Okay, these are all notations for the second derivative. So you see, so df dx is the first derivative, so d of that dx. So then you can write it this way that it saves a little time, or 2 primes. But this is still the rate of change of the rate of change of f with respect to x or y double prime. Okay? But it's the rate of change of the rate of change with respect to x. So what we're going to do is, so just jot down the notations, the rest, we're just talking about the derivative of the derivative. 5 different notations for it. So on your worksheet, we want to figure out, coordinate, that's what we're doing, we're coordinating between the first and second derivatives being positive and negative. So in this first row, the first derivative is positive. What would it mean for the accumulation if the second derivative is positive or 0 or negative? In the second row, the first derivative is 0. What would it mean for the accumulation in each case for the second derivative, and same with the third row when the first derivative is negative? So the conclusions here in this table are about the accumulation function, given the 2 situations coming together. Second derivative is 0, first derivative is negative. What would that mean for the accumulation function? So you're trying to coordinate those 2 things together. So these will be like little sketches of the accumulation function. Okay? So see how you do on that. Okay? Little sketches of the accumulation function given these 2 scenarios coming together. And I'm going to take roll.
Which wizard line in the second? That one. Oh, that one. Oh, you goes down.
Because we're trying to draw.
Okay, let me just interrupt you and let you work another minute after that. So in this whole first row, what can we say about the accumulation?
It's
Increasing. So if the first derivative is positive, it's increasing. And so what does that mean? So can we just make it in layman's terms? If the accumulation is increasing, then the graph is going up. So in your first row, the accumulation is going up because the rate is positive. Okay? If the accumulation is, or if the first derivative is 0, if the rate of change is 0, then what is the accumulation? Not changing. And so of course it could be a constant function, but usually it's, in these situations we're saying that it's not. So just for one moment, the accumulation is not changing. So we call this pause. Accumulation is pausing. For a moment, or not changing for a moment. And what about if the first derivative is negative? Then accumulation is decreasing. And so the graph is going down. All right, let's do the same thing for the second derivative. If the second derivative is positive, that tells us about the rate of change of the accumulation. What's the rate of change doing if the second derivative is positive?
going up.
Increasing, right? Or the rate itself, the rate is going up, right? Increasing. The rate is increasing, or the rate is going up. The accumulation is increasing more rapidly. That's right. Okay. What happens to the rate if the second derivative is 0? The rate of change. Pausing or staying the same for a moment. The rate is pausing for a moment, not changing. So again, what I'm writing now is about the rate. And finally, if the second derivative is negative, the rate is decreasing. And the rate is going down. Okay, take another minute to see if that helps. Okay? See if that helps. So let's not say going up or going down for the rate. I think that's confusing because you're thinking about a graph. So just increasing or decreasing. It's true, but it makes you think of the graph. Yeah. Of the accumulation. You're sketching little sketches of the accumulation that meet the requirements. Or just like a little part of a graph. So hopefully you got the corners right. That's the easiest. So hopefully you got the corners right. Those are the easiest ones. Did you get them right? So if you didn't get those right, then you're going to have trouble, okay? Those are the easiest ones. So what does it mean if the accumulation is increasing? So we're going up, and then the rate is pausing for a moment. What would that look like? Anyone think they got it? The rate is pausing for a moment. So it's kind of like for, yeah, but you got to make sure your accumulation is still increasing when you do that. No, it's increasing. The accumulation is increasing. Yeah, exactly. So he drew this. He went like this. So for a moment it pauses like that. So it's got to be increasing still. But for a moment there, the change in the rate is 0. Or the rate of change pauses. Do you see it? So then you could also have this. So we're talking about right there, or right there. Where the rate of change stops changing for a moment. It's, for just a moment it's constant, yeah.
Is it okay if we have just that section there, just a line?
Yeah, so a line going up is also this, but we're talking about curves. Yeah, so, but true. It could also be just a increasing line. But we're really talking in terms of curves. So in curves, we get these kinds of points just for a moment. Increasing, and for a moment it pauses. Okay? What about here when the first derivative is 0 and the rate is increasing? So if the first derivative is 0, it's pausing. What does that mean for the graph?
That the pause is like more, the slope of the pause is more positive.
What is the slope at the pause? 0, right? Accumulation is not changing for a moment. But our rate is increasing. So where does that occur? If the rate is increasing, it's becoming less negative or more positive. But then yeah.
I have a question. If the first derivative is 0, how can the second derivative be positive? Wouldn't it be just 0 too?
Mm-mm. No, it's when you plug an x value into the first derivative, you get 0. But then you get the second derivative, you plug that same x value in, it's not necessarily 0. So how can we have the accumulation pause while the rate is increasing? Yeah? Jonathan?
Well, it's when the accumulation is sort of like switching from decreasing to increasing.
That's it. So we're getting less negative, the rate's getting less negative, and then it's getting more positive. What happens there at that switch? What happens to the accumulation? It pauses. So what we get is called a local minimum. There's a pause while the rate is increasing. There's a pause in the accumulation. Accumulation holds steady for a second. All the while, the rate is getting less negative and more positive. You get a local min. Does it make sense? Okay, so what about how can the first derivative be 0 and the second derivative be negative? So how is the second derivative negative? when the rate is decreasing, right? Either getting less positive or more negative. So where there does the accumulation pause for a moment and neither increase nor decrease? Local maximum. Okay, similar to this, we got the same thing here, but we're decreasing. So it could be like this, or it could be like this. But you can't, it doesn't pause. The accumulation is decreasing all the while. The accumulation is decreasing all the while. But there's a moment there when the rate of change doesn't change. It pauses. You see that? Okay. Many possibilities for the way that the accumulation could be. So we're gonna many possibilities for both of them to be zero. Okay, so we need to kind of press on. So we'll see some of those possibilities. Okay, questions about the other 8? Does this make sense? Okay. So some terminology. Okay, what is a critical value of f? A critical value of f are these places where the first derivative is equal to 0, where the rate of change is equal to 0. And what do we say about that? What's happening to the accumulation at a moment where the first derivative is 0? Pause. So we neither get increase for a moment. There's neither increase nor decrease. So the accumulation pauses. Okay. Don't try to write this down. Okay. If you have a critical point, it tells us that the accumulation stops or pauses momentarily, either increasing or decreasing. Okay. It might continue to decrease or increase, or it might change from one to the other. If it changes from increasing to decreasing, then you have a maximum. If it changes from decreasing to increasing, the rate is changing from decreasing to increasing, then you have a minimum. Those are the two that we saw. So how could it pause? How could the accumulation pause but continue to increase, say? What would that be like? Think of x cubed. Do I have a picture of this? Sorry, pushing the wrong buttons at the wrong times. So think of x cubed. Here it's increasing, and what's the rate doing? Decreasing. So the accumulation is increasing, and the rate is decreasing. And then for a moment, the accumulation pauses. And then what does the accumulation do after that? It increases again. So this is a situation where it's a critical point, but it's not a max or a min because the accumulation is increasing before and it's increasing after. Does it make sense? And this is one of those possibilities where both the first and second derivative are 0 because there's a pause in the accumulation and there's also a pause in the rate. Here the rate is decreasing. And the rate pauses, and then the rate starts to increase, you see? So you're getting a pause in how much accumulation you have, and also a pause in the rate. Rate is decreasing, and then pause, and then the rate is increasing. Question?
Is it only pausing when it looks like it's almost horizontal?
It is, so for a moment it is horizontal. So accumulation pauses when the graph is for a moment horizontal. That's right. It doesn't change. It's for a moment, it's not getting greater or less, the accumulation. Okay, so a relative max occurs. A relative max or min occurs when you have a critical point, when you have that first derivative equal to 0, but that doesn't guarantee a max or min. Do you see? Because there's situations like this where it could be increasing and it's still increasing. And it's true that that the derivative is still 0. So what condition guarantees a max or a min? How do we know if so we get a critical point, we get the first derivative is 0, what guarantees that that is a max or a min?
So rate changes from positive to negative or negative to positive?
When the rate changes from positive to negative. Yeah, right. Okay, so here's two situations. We got a local max and a local min. And at each of those, it's a critical point. The accumulation is pausing because the first derivative is 0. So he said the rate, here the rate is positive, here the rate is negative. Here the rate is negative, and then here the rate is positive. So the rate of change changes sign. That's what he said. That's right. So the first derivative changes sign. Or the second derivative is not equal to 0. So that's not a condition that will guarantee that a critical point is a max or a min, is if the second derivative is not 0. What's the second derivative? All through there. All the while, the second derivative is, what is it?
Decreasing.
No, the second derivative. So the rate is decreasing. You're right, the rate is decreasing all through there. So the second derivative is negative. And all through here, the rate is increasing, therefore the second derivative is positive, not 0. Okay, so if the second derivative is greater than 0, means the first derivative is doing what? And which situation is that? This one, first one here, or second one here, that the second derivative is greater than 0? Second. Second derivative is greater than 0, concave up. So the first derivative is increasing, and you have a relative minimum. If the second derivative is less than 0, means the first derivative is decreasing, and you have a relative maximum. Somehow, we got through. We made it. I will post homework this afternoon. See you Monday. Keep coming to class. Don't miss class. Don't miss class.
That shows a lot of
Just telling you,